easy, or it's hard to tell how easy or hard it is. It looked easy at first, but I wasn't able to solve it that fast. So we have a point P, and we reflect it across each of the three sides to get A prime, B prime, and C prime.
Isn't this like the gliding principle?
It could be. Maybe it is just really easy.
So is that first triangle similar? That A prime, B prime, C prime?
Not to the original.
Oh.
But
And
yeah,
we can't do it. Then we can't do it like that.
Okay. Yeah, otherwise it would just be the gliding principle. So yeah, we reflect P. So I think the circumcenter of this triangle is like the isogonal conjugate of P, right? I think. So anyways, yeah. So we take the midpoints of A prime, B prime, and C prime. And it's supposed to be similar to the original triangle. So let's call this A double prime and B double prime. And this is C double prime. All right. Let's see if we can make it bigger. So yeah, maybe like that. And I kind of like that diagram. So yeah, there's a lot of flexibility here. Yeah, P can be any point it wants to be. And oh, I only drew this like halfway. Don't know why. Let me draw these all the way. So B prime, C prime. And yeah, these are not, this triangle is not necessarily, does not have its sides parallel to the original, but it's similar. Yeah. Maybe we could still use the gliding principle somehow. We just have to like do it in the other direction. So yeah, I guess then the question is, why doesn't the gliding principle in reverse work? Because they're oriented the same way. Yeah, why doesn't the gliding principle in reverse work? Or does it? Maybe I'm just, no, it can't. Because this is not similar.
Yeah, they are oriented differently. That's why.
That's why. A prime, B prime, C prime. Oh, I got tricked. I was thinking A double prime is like, yeah, they're not oriented the same. But maybe we could do some kind of reflection to make them.
Yeah, maybe we reflect and then do the gliding principle.
Yeah.
You know, when you use the gliding principle, you don't have to just take the midpoints. You can just scale it by whatever you want.
Yeah, it doesn't have to be midpoints. It could be any sort of factor.
Yeah.
So if I reflect D prime over A prime, this triangle, let's see what that does. So B triple prime. That's, and then almost looks like those concur. So let me try to make the diagram better so it doesn't look like that. All right. So then if we reflect B over B triple prime, or reflect, sorry, reflect about point. This triangle right here should be similar. If I call it like B quadruple prime, let me just call it K. Or I don't know, maybe B1. I don't know, I'll call it K. So this one we could try to show as similar to the original. So you're reflecting P over BC and then P over AB. And then you're defining this point as, let's see, so BK would be parallel to this, which is perpendicular to this. So yeah, we could define K to be the point that makes ABC similar to C prime K A prime. And then we could try to show like the collinearity. It's kind of weird, but it's one way to try to do it. So I wonder if this passes through the midpoint of A prime C prime. And maybe that's obvious. No, it doesn't.
I believe that most people just complex bash this.
Or just complex bash it, probably.
Yeah, since similarity is good with complex numbers, and there aren't any difficult things to compute.
I think someone
Midpoints are
on the
also
group
good.
might have already. I think someone on the group might have already done a complex bash, actually, like on the Facebook group.
Yeah,
So,
probably.
there has to be a synthetic solution, though. So let's see if we label this point right here, D B double prime is parallel to C double prime K. Yeah, like we have so many midpoints here. That would be parallel. Wait, is that right? No, I think I did the wrong. So PK be parallel to that. And I wonder if this is cyclic right here. I think it is, right? Because since this angle equals angle B, so this would be cyclic. So this is cyclic, and then we reflect P over this, P over this. So the reflection of P over B should also lie in this circle. That's not what I thought. Oh, it's not cyclic. This doesn't pass through A prime. I think it would be, that would be cyclic, but not that. But wait, shouldn't it be? Shouldn't this be cyclic? Oh, it must not be. So I'm getting confused because this is like almost an isosceles triangle. So I'm mixing up which things are similar to which things. But if we do the picture like that, yeah, then it's more clear. Wait a sec. What is going on? So this triangle is not similar to ABC. So what am I missing here? Right? This triangle was supposed to be similar to ABC by the gliding principle, right? So what did I do wrong? C prime. Yeah, what did I do wrong here? A double prime is the midpoint of that. C double prime is the midpoint of that, or the reflection. Then
Oh, you should reflect B over B triple prime instead of B prime over B triple prime.
oh, yeah, you're right. So this K has to go. I needed to do this instead. Interesting. It's my bad. So this should be similar to ABC. Yeah, that looks much better. Okay. Like that. Now K looks like it lies on. It's not going to be perfect, but there we go. Yeah, it's hard to get a perfect diagram. So there's just so many points. Okay. So B double prime is the midpoint of that. And what other midpoints do we have? How do we use that B double prime as the midpoint of that? So then B double prime. So yeah, if we draw B prime K, then this should be parallel to that. So B prime K is perpendicular to that.
And that is the Gauss line of BC, B prime, C prime.
BC, B prime, C prime. That is the Gauss line. So, okay, so BC, B prime, C prime. So we have C double prime and B double prime.
No, actually, it is A prime, A double prime, C double prime. That is Gauss line of A prime, C, A, C prime.
Yes. So this is like perpendicular to the Gauss line of that quadrilateral.
Yeah, and also B prime K is twice B double prime, B triple prime.
Yeah. Yes. In fact, is K the no? I was wondering if K is the circumcenter of that, but it's not.
So if we were to define K as that point which makes the similar triangle, which is well oriented and that stuff, then we would need to show that B prime K is perpendicular to the Gauss line, and then we would need to show that B prime K is twice, actually B prime K is then 4 times the distance from B double prime to the Gauss line.
Okay. Yeah. It's 4 times the distance from this to that. Tricky one. Yeah. Try to reflect and use the gliding principle. So yeah, basically, if you reflect this over this, then that over that, you're supposed to get something similar. I'm just curious what the circumcenter of this is, because I think whoever created this problem, maybe they were trying to use like isogonal conjugates. So yeah. So E is like the isogonal conjugate of P. And yeah, I'm not sure what we can do with that. So yeah, this is oriented the same way as this. Maybe we could use a homothéty, because like the midpoint of PA prime is this point, the midpoint of PC prime is this point. And so the midpoint of PK prime that's kind of interesting because it means that EF and the midpoint of this, which is G, is similar to ABC. So that might let us remove some of the diagram. So G, how did we get to G? G is the midpoint of PK, and K is the reflection of B over B double prime. And B double prime is the reflection of B prime. Oh, okay. So it's a little tricky. I mean, yeah, still a little tricky. But we kind of know angle PEF is angle PBF. So we have some angles there. Let's see. Those aren't collinear. Okay, so triangle EFK is similar to ABC. Sorry, EFG is similar, not EFK. And angle EGF equals angle B. So this is, so EBF and EGF have the same size circumcircle. A lot of interesting stuff here. So it's kind of interesting because it means if you reflect, there's a lot going on here, but if you reflect G over EF, then it means that these are all cyclic. And what else can we say anything about this point? Oh, that's kind of interesting. Those are collinear. So maybe this will help solve it. So
What's G?
G is the midpoint of PK.
Oh, okay.
I think if we could prove this stuff, then that might help solve it. Yeah, I'm sure we can erase a whole bunch of stuff here, but I bet if we could show G prime, P, and B prime. Okay, so we could start out by letting B prime P intersect this circle at G prime. And then we want to show, first we want to show G prime EF is similar to ABC. And that's probably just an angle chase because this angle equals angle B, and this angle is So yeah, this angle equals angle B. Can we show which one of these is angle C and which one's angle A? I don't even know. Let's see. One, two, three. 52. Is it this one or is it the other one? No, it's the other one. So can we show GEF is angle C? Well, GEF is GPF or G prime PF. How do we show that's an angle C? Oh, it's just an angle chase because G prime PF is angle C. Yeah, okay. So triangle G prime EF, we know is similar to triangle ABC. And so therefore, if we reflect G prime across EF, it still has to be similar to ABC. But now we might be able to apply the gliding principle. So then we reflect P over EF.
Wait, how do we know that the G prime EF is similar to ABC?
So first of all, so I'm defining.
So what are the definitions of points? Yeah.
Yeah. So here's what I'm doing. First, I draw B prime P, and I let it intersect the circumcircle of PEBF at G prime. That's how I first define it. So
yeah, then you can angle chase.
Yeah, then an angle chase shows that it's similar to ABC. So that would be step one. Step two would be I reflect G prime over EF. And then I reflect, so it's still similar to ABC. So GEF. And then I reflect P over all three of those. So then K A prime C prime is similar to ABC. And then I need to show if we define K this way, it's the same as I forget how we
that B triple prime is the midpoint of BK.
Yeah.
I think that's
Yeah.
Yeah. So maybe we should first try to show that BK in this definition of points is like perpendicular to A double prime, C double prime. Is that true even?
A double prime, C double prime. We want to show that B prime K is perpendicular to it.
Yeah.
Yes, it's true. So
wait, are B triple prime and K collinear?
B triple prime K and B?
Yeah.
Yes.
But what is B triple prime even? I forgot.
Yeah, it's the reflection of B double prime over A double prime, C double prime. I don't even know if we need B triple prime.
We need it for K.
Oh yeah, we do. Yeah.
Yeah. Okay, so B triple prime reflect B double prime and K is okay. We need to then by this definition of K, we need to show that K is the reflection of B over B triple prime.
Yes.
Okay.
Which I think is the same as showing B triple prime G is parallel to to beat P and it's half the length. So yeah, I don't know if I've made this harder or easier, but it's been interesting. Yeah, B double prime G. How do we get that? Yeah, this is tricky. Um, yeah. Um, okay, so B. Just so many midpoints, yeah. Yeah, probably vectors would be good for this too, right? But yeah, complex numbers might be even easier. I like that I found this collinearity, but yeah, I'm actually not sure how useful it is. It's kind of interesting. But I wonder if B double prime, I don't think it lies on that circle. So no. So we have to show that if you construct K in this weird way, it's the same as the reflection of B over B double prime, which does not seem that easy of a task. So you reflect P over AC to get B prime, then you take the midpoint, get B double prime, and then you reflect it. Yeah, see the reflection, the problem is the definition of B triple prime depends on the definitions of these two, which are not obvious. So that's really the issue with this method. Because yeah, you can't define B triple prime without defining these two, and these two are not that easy. One sec, guys, I'll be right back. All right. I'm gonna spend like 10 more minutes on this. It's a fun problem, but it's a little harder than I realized. Yeah, so, but yeah, that's one way to formulate it. We construct K in two different ways and we show they give the same point. I wonder if there's a way like to get what this line is without needing each individual point, A double prime and C double prime. Also, I wonder, is this cyclic? No. So if we draw PA, PB, and PC, then we have FA double prime is parallel to PA, and C double prime is parallel to PC. So we have three different parallels to PA, PB, and PC. So what if we just looked at that instead? We draw the three parallels to those three. It's probably an easier way to think about it. Now I'm thinking about using the gliding principle differently. So this is unlikely, but I wonder if P lies on. Oh, does P lie on this circle? That would be crazy. No. All right, another couple minutes, and then we will move on. It's tricky. So it's kind of interesting, like if we did it this way, EG prime FG would be similar to like A, B prime, C double prime, B triple prime, right? I didn't even think about that. So maybe we could use the gliding principle on those. But we have to figure out what have we proven and what have we not proven. So, and I don't think they're like, I guess you could, if you rotate it enough, you could say they're oriented the same way. So yeah, what if we try to use the gliding principle on both of these? It would be tricky. So we have F. So FA double prime is parallel to PA. And EC triple prime is parallel to PC. So I wonder if we could use that when we do the gliding principle. I don't know. If we want halfway there, halfway there. Okay, so the midpoints of EF and so this would be kind of interesting. So we take this midpoint and this midpoint, so HI. And then what if we took the midpoint of this and we took, I don't think this is going to turn out similar. Midpoint of this. No. Or we could try reflecting all of them across. So reflect. I reflect this over that. And let's see. This over that and this over that. And it's not going to do much. Okay. This over that and this over that. No, I don't know what I'm doing. All right, let's move on to the next one. I think the ones after might be a little easier. Let's see. We can come back to this if we get through the rest. Oh, this one actually looks kind of tricky. Let's see. So we have triangle ABC. And D, E, and F are the midpoints. D, E, F. X is the intersection of AB with the circumcircle. And we end up drawing tangents at B and C in the end. So I'll draw those eventually, but for now, we draw X. We're going to want to show something as a symmedian. This is X. Then we draw the circle through D and X tangent to ABC. So let's think about how to do this. So if it's tangent, we want the center to be on here. Basically, we want to do this. So it would be this circle. Centered at G. And hide this. And Y and Z are the intersections of the tangent at D with the perpendicular bisectors of DE and DF. Okay. So we want these to intersect the little circle, is that right? Maybe I did something wrong here. It looks hard looks like those won't intersect it. Unless you make it like a really, maybe they just want us to make it like a really obtuse triangle like that. That would be kind of interesting. Okay, let's try that. interesting. The tangents at D. Oh, it doesn't have to intersect the circle. It just has to intersect the tangent. Okay. So we have Y and Z. So this one would be Y. And this one would be Z. And I can make it a taller one again, because I didn't realize that. All right. Then we draw the intersection of YE and ZF. See where they meet. They meet at point P. G is the centroid of ABC. Oh, we're not really showing something as a submedian. We're showing okay, so it looks like we have a few other things to prove here. It looks like this is concurrent and this is concurrent. It's probably not that hard to show, I'm guessing. But we want to show that PG passes through the tangents at B and C. All right, let's clean this up. Whoops. So draw my tangents at B and C. Make it a taller triangle. So that I like the tangents to intersect below, ideally. Okay, shrink it a little bit. And there we go. Okay, so let's clean this up. I don't need this. Well, actually, I want the center of that circle. But so it looks like ZDF and YDE are isosceles. That's true by definition. So what are these lines? Now I'm just confused. I'm just gonna hide a bunch of stuff. Don't need this. But I do want to call this something better. Call it Q. And this is O. Okay, I'm hiding like everything here. It's just too much. Okay. So we have this. Then we draw the tangent at D. So it intersects the perpendicular bisectors at X and Y. So here's one. So this is isosceles, this is isosceles, and it's Y and Z. P is the intersection of YE and ZF. Oh, because I drew stuff as rays instead of lines. So like P disappeared. Okay, so this is P. This is P. And I wonder if PF is isosceles. It's probably be an angle chase to show that. Sure looks like it. So I think it is. And we want to show PG passes through H. And that looks like a homothety. Like it looks like, so PFGE, we want to show it's homothetic. And PEF is, it looks like G is just the incent well, it's not the end center, but maybe it is. Is G the end center of PYZ? I don't think so, because BG is not the perpendicular bisector of DF, so that shouldn't be true. G should not be the end center, but yeah, we just want to show homothency. And by an angle chase, PEF should be isosceles, because PFE is 180 minus CFE, which, and ZFD is ZDF.
Actually, one thing is that DEF, the 9-point circle, is the inner circle of PZY.
BZY.
That simplifies the problem a lot. But I didn't prove it yet.
DEF is the 9-point circle of BZY.
No, it is the inner circle of PZY.
Of PZY. Okay. Well, we could probably show. Actually, I think, yeah, like if we can show PEF as isosceles, then that would follow, right? Because PF equals PE, YE equals YE.
That is not practical.
Oh, what?
That is not something we could realistically do.
To show that PEF.
Maybe we could, but it would just be a column to showing that the 9-point circle is tangent to this small circle omega.
Yeah. Actually, I mean, it's obvious that DEF is the end circle, because Y, basically we're drawing the tangent at D, and then since like YE is tangent to the circle, since YD is tangent by symmetry, right? And same with ZF.
But we don't know that. We don't know that.
We don't know that.
Because we know that YZ is the tangent to the small circle, but not.
Oh, but not the other circle. Yeah, I got confused. You're right.
That's why I'm saying we need to show that 9-point circle and omega are tangent.
Or tangent. Yeah. Okay. So yeah, let me draw the 9-point center. This is N. Or maybe we could start the other way. We could start with the 9-point circle, draw the tangents, and then we could try to show that this is tangent to it. or that there is a circle through D and X that's tangent. So let's see, it would take X. So we'd have this point right here. So K should map to X. Oh, but a homothety at G takes, okay, so a homothety at G takes DEKF to AB XC. Interesting. So what does that homothety do to circle ABC? It takes DEFK. So it's kind of, I mean, it would kind of be the same as showing there's a circle through L and K. It's the same as showing there's a circle through L and K that's tangent at K here.
Okay, I proved that those two circles are tangent. It
Okay.
can be angle chased.
All right.
Then we should focus on proving the rest of the problem. So now we could basically delete circle omega since it doesn't do anything.
Well, once we know they're tangent, I think the problem's solved because basically PFGE is homothetic to like HBGC, right? We'd have to
Yeah,
show the angles are
looks good. Yeah.
okay.
Okay, so how would we angle chase? Basically, we can get that angle ZDX is equal to ABX because of the
ZDX
tangents.
is ABX,
ZDX, ACX actually.
ACX.
Yeah, that can be done by just observing the center of omega and homothety, which takes omega to the ABC.
Okay.
And then we can calculate angle FDZ, and that's it.
Okay. So ZDX, we do a homothety about Q that, or a homothety about X that takes.
Actually, just forget about homothety. We just have that DQ is parallel to AO, and X, Q, and O are collinear.
Okay. So then it follows that ZDX equals ACX.
Yeah, because ZDX, that is half of angle DQX,
Okay.
which is angle AOX, half of angle AOX.
Just half of angle ALX. Okay, that makes sense. All right. So So first we show that those two circles are tangent. So I'll just say label the points as shown. Well, first I'll show the. So
You know how they could have made this problem more cool?
how?
Actually, if the thing we needed to show was that PZXY is tangential triangle, quadrilateral.
Oh,
That would
really? It's
basically, yeah,
tangential.
that would basically trivially follow for what we have done, but it will be just much more cool since I didn't ever see a statement like that. Prove some random quadrilateral is tangential.
So, so there would be an in circle for PZXY.
Yeah.
Interesting.
Oh, actually, no. I'm stupid. Yeah. I just no, it isn't true. But if you took some other tangent, then it would be true. Okay.
All right. PQX over 2, which is equal to angle AOX over 2. Over 2, which is equal to angle ACX. And so that implies that these circles are tangent. Let me think about that. Because ACX intercepts the median AX here. And so that would basically equal angle DFK, which is angle KDY, or equals angle DFK. Yeah. And so this implies DZ is also tangent to DEF. Fine DZY is also tangent to DEF. And once we know that, then the problem's not too hard. So ZD equals ZF and YD equals YE. And that means that DEF is the in circle of PZY. Okay. And once we know that, then a homothency at G takes PFGE. So yeah, I guess there's a little more work. We just need to show these are similar, but that shouldn't be hard. So PFE is similar to HBC. Because so HBC is angle A, and this angle we want to show this, or we want to show this angle is angle A. But angle PFE is angle FDE, which is equal to angle A. So angle PFE equals angle FDE equals angle A. And this means that PFGE and HCGB are homothetic at G, and that implies PG and H are collinear. And that basically solves the problem. And that implies, yeah, I'll just end it there. Yeah, so not really that long of a solution. Let's see. Oh, this is like a conditional problem. Let's try this. See what we can do. So we have a half hour left. We have a triangle ABC and we take the midpoints. Okay. So we have D and E. F. D is the midpoint of EF. So we want to reflect. This is F. And then we draw the circumcircle of FBB. So AFBE is a parallelogram. We have a couple parallelograms here. This is on CD, and so the midpoint of BG lies on the circle. Okay, so that's kind of defined in a weird way. How do we draw that? We want a point on CD so that the midpoint of that segment lies on the circle. Another way to say it is we want, I think I know how to do that. We would take the midpoints of these and we see would be this point right here. But we need to rename stuff. So this, we'll call this M and N. And then this would be G. And H is the intersection of this circle and FC. And we want to show BHGC is cyclic. That doesn't look true in this diagram, so maybe I made a mistake. Oh, G
is on
is the point on
CD.
CD, sorry.
And also I saw this is like trivial.
Oh, it's trivial?
Yeah.
Okay, so it's too easy then. Let's see.
The only thing we need to notice is that F, M, and N are linear.
Okay. Is that, let's see, that's probably that's probably obvious because this is a parallelogram, I'm guessing. So
Yeah.
FB.
Yeah.
Okay, so then these are collinear, and
then you have angle BGC is BXN, which is 180 minus FXB, which is 180 minus FH.
And that solves it. That's
Yeah.
too easy. So, should I even type that up? That would just be for the viewers. I'll move on to the next problem. I respect your time enough. I don't want to just waste it. So this is like a conditional problem. I think I might have done something similar to this actually really recently. So it has the in-center and the circumcenter. Yeah, I think that last problem was probably like a junior problem. So draw D and F. that if the line parallel to EF through I, so we draw a parallel line here, and the line parallel to AO through D, that's kind of interesting. Parallel to AO through D, and the altitude from A. I don't know if this is exactly like the problem I did. Are concurrent. So if these concur, then they concur at the orthocenter. Interesting. All right. So DG is going to be parallel to AO, and AG is the altitude. Call this K. And IG is parallel to EF. So if M is the midpoint of BC, another way to say it is that AG is twice OM. We could also do it that way. We know that IM bisects AD. All right. So it looks like, it looks like in this configuration that it's going to keep calling things H, but it looks like BP might be perpendicular to EF. Oh, that's not true. In fact, it's really that. To draw this point, looks like DH is perpendicular to EF. Or I could call this Q. And is this like the topmost point? Looks like that might be true. Yeah, interesting. So it looks like in this particular situation, it's like AO and D prime are collinear. I haven't proven any of this stuff, but it looks like it would be true. And these are isogonal. So yeah, this is a special kind of triangle, obviously. Maybe IO is, I was going to say maybe IO is parallel to BC, but I don't know about that. So let's see. So I mean, AQ is equal to QG. Yeah, there's a lot of stuff we haven't proven here. I think the key is using IG as parallel to EF. That would mean that AIG is a right angle. So could we do anything with that? When we draw the circle, this circle, maybe there's something special about this point. It keeps calling everything H, unfortunately. But it looks like that point and M. I don't think this is the antipode. Oh, maybe it is.
That's just by
Oh yeah, if this was the
Like
orthocenter,
cube
that would be the known property. Yeah.
yeah.
So that's another way to think about this. This, this, and this. So how do we use that IG and EF? So we use that because that would mean this is a right angle. And if that's a right angle, then this is a right angle, then N, G, and R are collinear. So basically we need to show the line NGR passes through M. We don't really need B prime if we don't want. Yeah, if we can show that N, G, and M are collinear, that would solve it. So we use the parallel. Altitude and the line. And we need to use that this is parallel to AO. So DG is parallel to AO. So DG is parallel to AO, then we could let it cut. So then like GS is parallel to AR. Let's see. Is it obvious that GM equals MR? Well, that would mean that would be Trifty's the orthocenter. So that would okay. So yeah, really, yeah. Once we use this, That might help solve it. How do we use that parallel? That's the key here. Well, if they're parallel, then angle DGK is MQK is IQG, which is twice IAG, which is twice 90, which is 180 minus twice this. Oh, so that's equivalent to saying GI bisects AGD.
How did you get that?
Just a long angle chase, but
Okay, then we're finished. I proved that GI bisects AGD.
Oh no, I'm saying the information that we're given is equivalent to, but like that doesn't prove it. That's something I inferred from the problem.
Oh, okay.
Yeah. Okay. So it's basically the problem is equivalent to showing you start with the in-center, you take the perpendicular, and then you want to show, then you draw so that like this would be the angle bisector, and then you want to show this as a tangency point. Yeah, the converse of this would probably be so easy, but okay, so that's the same as saying this line. So let's draw IG. It's the same as saying that this angle equals this angle, which yeah, like maybe I should draw this line all the way. So this angle equals, so UAI is equal to AGI. So is that right? So it's like UAI is isosceles kind of. Yeah. like this. That should be true. H1. So yeah, we're getting there, but we're not there yet. Center. See, what else do we notice? There's probably a whole bunch of things going on in this figure. It's just proving them in the right order. So there's a lot of stuff that could be true, but yeah, my diagram's not exact, so.
The problem condition is equivalent just to ID bisecting AO.
ID bisecting AO?
Yeah.
Yeah, okay, so that would mean that D is the midpoint of KM.
Yeah. Wait, it doesn't look like that.
Yeah, I don't think that's right, because that would mean IQ is IM, but that's not true. The IQ is a radius, but so yeah.
Yeah. I made a mistake.
Sorry. So QH is parallel. So QHIG is a parallelogram. That we know.
Okay, now I know what is equivalent actually. So if you reflect AI, A or I,
Okay.
then because we know that GI bisects angle AGD, and also since GI is perpendicular to AI, then we know that GD and A prime are collinear.
Okay. Yes.
And now when you define H as the intersection of DI and AO,
okay,
since we know that the DA prime is parallel to AH, and also AI is equal to IA prime, then we have that ID is equal to IH, or equivalently that H is on the incircle.
Okay.
And from here we can actually do stuff, because this condition that H is on the incircle is actually good.
Okay. And then we know that this is a parallelogram. And I wonder if that just solves the problem. Yeah, we're pretty close. So that's equivalent to saying IH equals OM. And then I think like I feel like okay, so basically I can delete point U. And I can delete S. But, okay, so let me follow what you're saying. Reflect A over I to get point A prime. And then G, D, and A prime are collinear. And then AI is IA prime. And so if we like hid this circle, you said we know that ID equals IH. I'm trying to remember how we know that.
Because dA prime and AH are parallel.
Because dA prime and AH are parallel. Okay. Wait, so this equals this. And then we take two parallel lines. Okay. So that's where we use that fact. I think this is enough to solve it. Just be a matter of typing up stuff, but because then, like once we know all that, we know that IG is parallel to QH because AO.
But what is the definition of Q?
Q is where the altitude intersects the circle.
Okay.
So we know that QH is parallel to EF since AO and the altitude are isogonal.
Yeah.
So QHIG is a parallelogram. So like HI is equal to QG, which is half of AG. Oh, I'm not.
How do we know that it is half?
Oh yeah, we don't. How do we know that Q is the center of that circle? That's a good point.
Well, actually, we know that we have a 90-degree angle.
So yeah, this is 90 degrees. But how do we
You
know that?
You don't need the circle at all. We can just work with like Q. Since AIG is 90, then QI is equal to QG, and it is equal to QA.
QI equals QG. How do we know QI equals QG?
Oh yeah. I also just suppose that it is the center.
Okay.
But okay, we may be able to do this. Can we show that IQ is parallel to AH? I think yeah. Since Q is the reflection of H in AI, right?
Yeah. Yes.
And then we can have that angle. We have that angle AIH. It is equal to the angle QAI, since we have IH and AK parallel.
Yeah.
And that angle QAI is IAH.
Yeah, you're right. So yeah,
And that's it.
we need this point P. I don't think we need this point J. So yeah, I could try to type it up quickly. But yeah, like we know that basically we know that this is a rhombus and this bisects. Sorry, we know this is a kite and this bisects it, so it has to be like a rhombus. So I think this like also has to be a rhombus. I'll type it up quickly, but let A prime be the reflection of A over I. By an angle chase, I'll just say by an angle chase, GI bisects AGA prime. select that. And GI is parallel to QH, so this is a parallelogram. And this, are we given? So GI bisects that, and this is a parallelogram, and so AQIH is a kite. We know that. By symmetry, AQIH is a kite. But then these are all parallels. QH is parallel to EF is parallel to IG. And how do we know this is parallel to IM? I forgot that.
We don't need that Q, I, and M are collinear.
We don't need that. Interesting. Okay. We even need point M? Maybe not.
Maybe just for that part of showing it is the orthocenter. That OM is
Half of AG. Yeah.
Then maybe we need to prove Q, I, and M are collinear.
Okay. So AQIH is a kite. And QHIG is a parallelogram. So IG. So we have a parallelogram and a kite. Yeah, can we show QI is parallel to AO? So line parallel. So DG is parallel to AO. And we want to show QI is parallel to AO. But if we know this is a
You
kite,
can angle chase that, right? Since
yeah.
Q is the reflection of H in AI.
Yeah, so QI bisects, yeah, so like this is a kite. So from there it follows that Q is the, yeah, I think we've got it, but let's see. I'm just confused. So QI, we know GD is parallel, but QI we can show as parallel just by an angle chase. Oh yeah. So basically, since basically we want to show this, do we know DIG is isosceles? I keep going in circles, sorry. But by an angle chase, I think, yeah, I think it's just angle chasing. So DIG is isosceles, and DG is parallel to AO. So since IHQ is isosceles and HQ is parallel to IG, yeah. So so since DIG, how did we know that was isosceles? Sorry, just so IHQ is isosceles. Whatever. I think we can stop it here, but because we're a little bit over, but I think we're really close. So you might have figured it out, and I might just be confused, but
I think it just it is left just to write those angle traces, but we are basically done.
okay. So by an angle chase, IQ is parallel to AO. Oh, and And that implies Q is the midpoint of AG. That means that AG equals OM. Well, no, Q is the midpoint of AG. Implies AG is 2 OM. Implies G is the orthocenter of ABC. All right. We'll stop here. What is going on with it? Oh, that was the problem. All right, so thank you both for sticking around, participating, and for everyone watching on YouTube, thanks for watching. If you want to join us in the future, feel free to email me at mgreenb801@gmail.com. We meet every Sunday at 8 a.m. US Central Time. So thanks again, and have a great day. See you next time.